In this lesson, we're gonna learn how to solve 3D systems just by using moments instead of summing up forces along X, along Y, and along Z. Now this will help us save time in some problems, especially when our loads are applied at an eccentricity. And so last time, these were the results that we obtained by summing up forces along X, along Y, and along Z. But here, since we are interested in forming our solutions just by using moments, then our first step will be to transmit all the loads here at joint A. And so we can transmit these loads at these points, B, C, and D. And so transmitting this load, its line of action will pass to this support. So we have this one for AB. Again, we are just transferring this one up to here. And then for AC, we have this line of action. And then for AD, we have this one. And so we will now resolve these loads into their respective components. Now for B, since we have already discussed that for AB we only have components along X and along Y because this doesn't have a Z component, then our forces will also be along X and along Y. Now the horizontal component of this load will be acting to the left. So we have this component, let's say this is BX, and then our component along Y will be acting downward. So we have this one, this is BY. Now for the load at C, we have a component acting to the right for the horizontal component, and then for the component along the Z axis, we have this one going forward. Because if you'll try to see the direction of this load, it's acting forward, and then it's acting to the right, while it's also acting downward. And so this means that our CY will also act downward. So this is CZ, this is CY, and this is CX. Again, this is pointing downward, it's pointing forward along the Z-axis, and it's pointing to the right along the X-axis. While for this load, we have this one pointing downward and pointing backward. So for DY, we have this direction. Let's just make this AB, ABY, this one AC, and then here we have ADY, and then for the Z component, it will be acting backward. So we have this as our ADX. And so these are the components of our loads right here, which were transmitted from this joint. Now for 2D systems, we need to take moments about a point to obtain the reactions of our system. However, for 3D systems, we need to take moments about an axis. Now you can choose any 2 points where you can take moments. Now we can label this point as point O. And so for my first equation, I can take moments about the Z-axis. And then we'll set this one to 0. Now this is our Z-axis. Now, in taking moments for 3D systems, we need to exclude the following. We need to exclude forces parallel to the axis and also forces that directly hit the axis along their line of action. And so let me just move this. We always need to follow this rule. So taking moments about the Z-axis, we'll exclude ABX. Now why? If we'll extend the line of action of ABX, it will hit our Z-axis. So that's why this will be excluded. Now for ABY, since it has a moment arm up to the Z-axis, which is 5 meters, we'll be including that one. Now, if this is our moment center, and then we'll be applying this load, then our figure will rotate counterclockwise. So this is gonna cause a negative moment. So minus ABY, let's multiply this by the moment arm of 5 meters, which is this perpendicular distance. Again, this forms a 90-degree angle. Now, let's try to look at point D. Now we have ADX. Now if we'll extend the line of action of this reaction, then it will be parallel to the axis. By the way, this is ADZ. And so since this force is parallel to the axis, the Z-axis, where we are taking moments, then it will be excluded, abiding by this rule. Now for ADY, the line of action of ADY directly hits the Z-axis. And so that won't cause any moment. Because again, we don't have any perpendicular distance about the Z-axis. Now finally, let's try to look at point C. Now for point C, the line of action of ACX will directly hit the axis if we'll extend it. And so this will be excluded. And then ACZ is parallel to the axis. And so this will also be excluded. And so what we'll only include is ACY. Now about the Z-axis, ACY will cause a clockwise rotation. And it will have a moment arm of 2.5 meters. So this will be plus ACY multiplied by the moment arm, which is 2.5 meters. Now, aside from these loads, we must also look at the external loads. Now, for this one, if we'll extend the line of action of the 1000 Newton load, it will extend up to the Z-axis. And so that will be excluded. However, for the 100 Newton load, it will have a moment arm of 8 meters about the Z-axis. And so we're going to include that. Now, about the Z-axis, the 100 Newton load, which is acting horizontal, will cause a clockwise movement. And so we have plus 100, the force, multiplied by the moment arm, which is 8 meters. So times 8, this is equal to 0. Now let's try to sum up moments about another axis. Now we can't do it about y because we will have too many unknowns. And so what we're gonna do is we'll take moments about the x-axis. And so now, we're gonna take moments about this axis. Now let's try to look at point A. Now for point A, the line of action of ABX is parallel to the x-axis, and so we'll exclude that. Now for ABY, its line of action directly hits the x-axis, and so it will also be excluded. Now if you will look at point D, the line of action of ADZ following this rule will hit the x-axis. Again, extending this one will directly hit the axis, so that won't have any moment arm. However, for ADY, it will have a perpendicular distance of 5 meters going to the x-axis. And then since I assume this as the positive direction, then any moments going to that point will be considered positive. And so we have ADY multiplied by the moment arm, which is 5 meters. This will be positive. And so we'll now look at point C. Now the line of action of ACZ, now let's just make this parallel to the z-axis. Its line of action, when extended, it will hit the x-axis. And so this will be excluded. And then since ACX is parallel to the x-axis, it will also be excluded. And so what's gonna cause a movement is only ACY. And so here we have ACY multiplied by the moment arm, which is 2.5. It will cause a counterclockwise rotation about this axis because our movement will be towards this direction, which I assumed as negative. So we have minus ACY multiplied by the moment arm, which is 2.5 meters. This is gonna be equal to 0. Now we won't include the external forces because the 100 Newton load is acting parallel to the x-axis. So we'll exclude this one. And then for the 1000 Newton load, if we'll extend the line of action up to this point, then it's gonna hit the x-axis. So it will also be excluded. And so we now have two equations with two unknowns. And so we can now solve ABY as well as ACY. But to make this more holistic, we can add another equation, which is the summation of forces along y. So summing of forces along y, we have the forces acting downward equal to the forces acting upward. This will be ABY plus ACX plus ADY. This is gonna equal to 1000 newtons. Again, we are equating downward forces equal to the upward forces. And so with these three equations, we can now solve ABY, ACX, and ADY. So here we have mode, and then equation, press 5, and then press number 2 for 3 equations, 3 unknowns. And so we're gonna treat this as our A, this one as our B, and this is our C. And then the constant term at the right side, let's consider that as our D. And so we're gonna rearrange this one. Let's move this to the right side. This will become minus 100 times 8. So minus 100 times 8, this will define our D. So we have here, for A, we have a coefficient of negative 5. So minus 5, and then plus 2.5 for B. And then for C, since it corresponds to AD, and we don't have any expression containing AD right here, the coefficient will just be 0. And then for D, we have minus 100 multiplied by 8. Now for the second equation, we have ADY multiplied by 5. So this will correspond to C. So we have positive 5. And then for AC, our coefficient is negative 2.5. Now let me just rearrange this one. Let's make this minus ACY times 2.5 plus ADY multiplied by 5. So again, this is minus 2.5. And then since we don't have a term containing ABY, let's not include this one. Now by the way, this is also ACY. And then for the third equation, we have all the variables equal to 1000. So we have here 1, and then 1 for ACY, and then another 1 for ADY. And then this is gonna equal to 1000. So press equals, we're gonna get all the forces. So we have ABY equal to 370, and then press equals, we have y equal to 420. This is ACY, since it corresponds to our second unknown. So ACY equals 420, and then press equals, we have ADY equal to 210. However, these forces are not the ones we are looking for, because again, we need to have these values. And so how can we get the force in AB, AC, and AD just by using these values? Notice that these are the y components of our tension forces. And so let's move this. This means that if we'll take the y component of AB, we're gonna obtain the value of AB. So here we have AB times the y component, that's gonna equal this value. So AB times, for AB we have y equal to 8, so 8 divided by the length, which is square root of 89, this will equal 370. And then for the second one, we have AC multiplied by the y component, which is 8, divided by this value, 3 square root of 34 divided by 2. This is gonna equal 420. And then for the last one, we have AD multiplied by the y component, which is 8, divided by the length, which is square root of 89. This will equal 210 newtons. Now let's first try to solve AB. So we have AB times 8 over square root of 89 equals 370. We have AB equal to 436.32. And then for the second one, we have AC times 8 over this value, so 3 times square root of 34 divided by 2. This is gonna equal 420. And so we have AC equal to 459.19. And then for AD, we have X times square root of 89 equals 210. Solving AD, we have 247.64. And so notice that these are the same with our previous results. However, in here, we were able to streamline the process because we only used moments instead of summing up forces. And so this is an alternative if you want to be more efficient with your solutions. Again, just transmit the loads, and then when taking moments about an axis, always exclude forces parallel to the axis and also exclude forces that directly hit the axis if you will extend the line of action. Now, to make our discussion more holistic, let's try out this example wherein the applied load is not directly at the joint, and then we also have another support here at O, which is a ball and socket support. And so what we're gonna do first is we'll assume the directions of the tension of cable AC, this one, and also cable BC. And then here at the support at O, we will have 3 reactions, because for ball and socket supports, we have one reaction along X, another reaction along Y, and another reaction along Z. And so that's why we'll have 3 reactions. Now the direction of the reactions won't matter, because if our assumption is wrong, our results will just come out to be negative. And so at point O, we have OY, which I will assume will act upward. Again, our assumption here won't matter, because if we'll get a negative sign, then the direction will be opposite to our assumption. So this is OY. And then for OZ, the reaction of O along the Z-axis, let's assume it's going to the right. So this is OZ. And then for the reaction of O along the X-axis, let's say it's also going to the right. So this is OX. Now, since we are applying a downward load right here, we know that BC and AC will carry tension forces. So this is BC and this is AC. Now we can actually transmit this load up to point A. Again, this is the line of action. And then for BC, we can transmit it up to point B, because if we'll extend the line of action, it will pass through B. And so let's just move this one. This is BC and this is AC. And so let's try to look at the components of this force. Now for AC, along the X-axis, it's going to the left. So here we have parallel to the X-axis, this is gonna be ACX. Now parallel to the Z-axis, the direction of this force is going to the left. And so we have here ACZ. And then for the Y-axis, it's going upward. So here we have ACY. And so let's try to look at point B. Now for BC, the component along the X-axis is going to the left. So here we have BCX. This is parallel to the X-axis. And then along the Z-axis, this is essentially going to the right. And so we have here BCZ going to the right. And then for the Y component, it's actually going upward, since this is going upward. So we have BCY pointing toward this direction. And so we now have our forces. We have the components of BC, AC, and also the reactions at O. So we can now take moments. Now let's say I'm gonna take moments about the y-axis to form an equation. So we have summation of moments about the y-axis. This is our line. And so let's recall our rule. In taking moments, we'll exclude the following. And so taking moments about the y-axis, this line, we're gonna exclude ACZ, because if we'll extend the line of action of this one, it's gonna hit the y-axis. And so this is excluded. And then we're also gonna exclude ACY, because this is parallel to the y-axis. Again, this is y and this is y, so that will automatically be excluded. And so what's gonna cause a moment about the y-axis is the force ACX, and it will have a moment arm of 4 meters. So we have, let's assume that this is the positive direction while this is minus. So applying this force, let's take this as our moment center, it will rotate clockwise. And so that's gonna be plus. So we have ACX multiplied by the moment arm, which is 4 meters. Now let's look at point B. For the components of BC, we're gonna exclude BCZ because its line of action will directly hit the y-axis at this point. And then we're also gonna exclude BCY because it's parallel to the y-axis. And so what's gonna cause a moment is only BCX. Now for BCX, our moment arm up to the y-axis is 3 meters. And then it's gonna cause a counterclockwise rotation about the y-axis. So this is gonna be minus BCX multiplied by the moment arm, which is 3 meters. And then for the external load, the applied load is parallel to the y-axis, and so that's not gonna cause any movement. And so this is now equal to 0. Now for the next step, I can take moments about the z-axis. Now sir, why not the x-axis? If I'm gonna take moments about the x-axis, then ACZ and ACY are both gonna cause movements about that axis. And so we will have a lot of unknowns, which we don't want. And so here, taking moments about the z-axis, this is now our line. Now considering point A, the components of AC, we have ACZ, which will be excluded because it's parallel to the z-axis. And then we have ACY, which will also be excluded because extending the line of action will hit the z-axis directly. So what's gonna cause a moment is only ACX. And then if this is our moment center, and we will apply this force, it will cause a counterclockwise rotation. So we have here minus ACX multiplied by the moment arm, which is this perpendicular distance. So that's gonna be 3 meters. Again, this is perpendicular. Now for the components of BC, this is gonna be excluded because it's parallel to the axis, while for BCY, its line of action will hit our axis of interest. Now only BCX will cause a moment about the z-axis, and then the moment arm is still gonna be this distance, which is equal to 3 meters. So we have here, this is gonna cause a counterclockwise rotation about the z-axis. So we have minus BCX multiplied by 3. And then we're gonna look at the external load. So about the z-axis, this is gonna cause a moment. And then our moment arm is this distance. So that's gonna be 5 meters plus 2 meters. And then this is gonna cause a clockwise rotation about this axis. So this is plus the load, 1000 newtons, multiplied by the moment arm, which is 7 meters. And so this is equal to 0. Now rearranging this equation, I can now apply two equations to unknowns. So moving this one to the right, it will now become negative. So this is minus, and then let's just remove 0. And so I can now solve ACX and BCX. And so we have mode, and then equation, pick one. Let's treat this as our x, and this one as our y. And then our coefficients will correspond to A and B, while the constant term will correspond to C. So we have 4 minus 3 equals 0. And then for the second equation, we have minus 3 and also minus 3. That's equal to minus 1000 times 7. So we have press equals x equal to 1000. So ACX equals 1000 newtons, and our BCX will be 4000 over 3. Now this is approximately 1333.33, and then this is newtons. And so we can now solve AC and BC for the first and second question. Now how are we going to do that? We need to first take the components of AC and BC. So we have here X, Y, and Z. We have AC and BC. Now for AC, our component along the x-axis, this one, is 5 meters. From this point up to this point, that's going to be 5 meters. So 5. And then our component along the y-axis, from this point up to this point, the vertical distance is gonna be 3 meters. So 3. And then for the z-axis, from this point up to this point, the distance along the z-axis, this one, that's 4 meters. So this is 4. And so our length is gonna be square root of 5 squared plus 3 squared plus 4 squared, which is gonna be 5 square root of 2. And so we're gonna store this into A to streamline the process. Now for the second one, for BC, our x component is gonna be the distance along the x-axis, this one, from this point up to here. So that's still gonna be 5 meters. And then for the distance along y, that's also gonna be 3 meters. And then for the z component, from this point up to this point, the distance along this axis, the z-axis, this is parallel to the z-axis, that's gonna be 3 meters. So 3, we have the length equal to 5 squared plus 3 squared plus 3 squared. So we have here square root of 43. And so we'll store this into b, this value. So shift store and then b, we have the following. This is a, so 5 square root of 2 equals this value. So shift store a. And so since this is the x component of AC and this is the x component of BC, we can get AC and BC by using these ratios. So we have for AC, let's multiply this by the x component, which is 5 meters, divided by L, which is stored into A. This is equal to 1000 newtons. And then for the second one, we have BC, the resultant force, multiplied by the x component of BC, which is 5, divided by the length, which is stored into B. This is equal to 1333.33. And so solving AC, we have x times 5 over A equal to 1000. We have 1414.21. So AC equals 1414.21 newtons. And then solving BC, we have x multiplied by 5 over B. This is equal to this value. So we have BC equal to 1748.65. So BC equals 1748.65 newtons. And so we now have ACX and BCX. Now since to solve O, we need all the forces, these 3 components, and also this one. We need to get ACY, BCY, as well as ACZ and BCZ. So getting ACY, we have AC multiplied by the Y component, which is 3 meters, divided by the length, which is stored into A. And then for BCY, we have BC multiplied by the Y component, which is 3 meters, divided by the length B. So this is gonna be 1414.21 AC times 3 over A. We have 599.99, which is 600. So 600 newtons. And then for BCY, we have 1748.65 multiplied by 3 over B. So that's gonna be 800. So 800 newtons. And then for ACZ and BCZ, we have AC multiplied by the Z component, which is 4, divided by the length, which is stored into A. And then here we have BC multiplied by the Z component of BC, which is 3 meters, divided by the length B. So here we have 1414.21 times 4 over A. This gives us 800. And then for BCZ, we have BC multiplied by 3 over B. This gives us also 800. So this is 800 newtons. And so we're gonna label our forces. So this is ACZ, which is 800, and then BCZ is also 800. Now ACX is 1000, and then BCX is this value, 1333.33, and then BCY is 800, while ACY is 600 newtons. Now to get the magnitude of the ball and socket support reaction at point O, we need to get the resultant force. So we're gonna sum up forces along the z-axis, along the x-axis, and also along the y-axis. And so summing up forces along the y-axis, we have positive 600, since that's going upward. So 600 plus 800, and then minus 1000 plus OY. We can now solve OY. So we have here 1000 minus 600 minus 800. This is gonna give us minus 400, which means that our assumption is wrong. So OY is actually pointing downward. So here we have OY equal to 400 newtons pointing downward. And so we'll also sum up forces along the x-axis. So we have OX pointing to the right, so that will be positive OX. Again, this is my assumed positive direction for X, and this is minus, while for Z, this is positive, and this is minus. And then for the y-axis, this is plus, and this is minus. Now your assumption may be opposite, but we'll still be able to get the same results. So here we have OX minus ACX, which is 1000, and then minus this value. And so this is going to be equal to 0. So we have 1000 plus 1333.33. We have this value. OX equals 2333.33. And then since we have positive, this means that our assumed direction is actually correct. So we have this one pointing to the right. Or let's just use this direction it's a bit inclined. Now finally, we're gonna sum up forces along the z-axis. So we have minus 800 because this is my assumed negative direction along the z-axis, and then plus 800 because it's pointing toward the positive direction, and then we have OZ pointing to the positive direction. So plus OZ equals 0. OZ is gonna be 0 newtons. Now to get the reaction at O, we need to get the resultant force. Now since we have three components, we have OX squared plus OY squared plus OZ squared. So this is gonna be this value squared plus 400 squared and then plus 0 squared. So we have here 2367.37, and then this is newtons. Now as your practice, try to solve the same questions but change this one into 1 meter. I'm gonna post the results in the comment section. So again, this is for number 1, force in cable AC, and then RO is the magnitude of the ball and socket reaction here at point O.